All right, so do you have any question, David?
Not on the material that we had for the midterm.
All right, yeah. So I will record the video with the midterm solution today, and I might upload it today or tomorrow. And if
Okay.
you have any question, just let me know. All right, so let's start a new chapter, which is the kinematic of rigid bodies. And our first section in this chapter is the planar rigid body motion. So chapter 16.1, planar rigid body motion. So when we talk about rigid bodies, so we mean that the body doesn't deform. So let's make it clear. Rigid body means doesn't deform. So for example, my calculator, this is considered rigid because it doesn't deform in this way or either this way or any other direction. So this is considered a rigid body. So when you push this body and you make like a fixed point, it will do a rotation. So all the forces will be translated in a kinetic energy and allows this body to do some rotation. But for example, if I get my ruler is considered a little bit rigid in this direction, but it is not rigid in this direction. So all our principles for rigid body cannot apply in this direction, because we assume that when you put a force on a rigid body, it will cause some rotation. But when you do it on a flexible body like this way, it will do some deformation along with rotation. So it will deform and rotate. So this will not be a rigid body. So that's the meaning of rigid body. It means that the body doesn't deform. So let's characterize the motions of the rigid bodies. So before we had particles, something like this, and this is a very small. And today we will be having something like that, and this is called rigid body, and it's a big body. So at the particle, we didn't study the rotation of the particle about itself. Like imagine that you have a small marble and like you are trying to rotate the marble around itself. So it is not a motion. So what we were studying is the translation of the particles. But with rigid body, you will have different types of motion. Like this body could be translating and could be have a linear or a rectilinear translation, like this body is like this and is moving this way. But if you could have this body is moving on a curve as itself, and we call this as a curvilinear translation. So the body is not rotating, just like moving on a curve. Or this body could be fixed at some point, like this, and keep rotating about this point, and we call this fixed axis rotation. Or it could have a combination between these motions, like it could like rotate and translate at the same moment, like it could rotate like this and translate. So let's write this down. So we have number one, rectilinear translation. So for rectilinear translation, you have your rigid body something like this, and this is point A, and this is point B. And this body will be moving, translate like this, or any direction like. And you will have here, we call this at least VA and VB, and all of these are vectors. And for rectilinear translation, VA is always equal to VB in magnitude and direction. So they should have the same magnitude and same direction, because if one is bigger than the other, the rigid body will rotate. So they should have the same magnitude and the same direction. And the omega of the body will be equal to 0, because if the body has an omega and is rotating about a certain point, so it will not be a rectilinear translation anymore. So it will be having a fixed axis rotation, or general plane motion, like it's rotate and translate in the same time. So omega is equal to 0 and alpha is equal to 0. And this is the angular velocity. And we sometimes call it theta dot, and this is the angular acceleration. And this is theta double dot. And the normal acceleration of this body is equal to 0 as well, because it doesn't rotate on a curve. So there is not a normal acceleration component. So this is for rectilinear translation. And after, like, let's assume that the body will get here, and it should be the same body at this point, and it will have VA vector and VB vector. So it will just translate. So let's get to the second type of translation, which is curvilinear translation. So for curvilinear translation, you have your body like this, and this is point A and this is point B. So it will move on a curve like this. And it should be here. And your body will come, for example, here. And if you have VA vector, and here's VB vector, and you will have here V, let's see, VA1 and VB1, and here you will have VA2 vector and VB2 vector. So for this type of motion, VA1 will be equal to VB1. So this 2 is equal in magnitude and equal in direction. And also VA2 will be equal to VB2. Here will be equal in magnitude and direction. However, this body doesn't have omega. It doesn't rotate about itself, but it rotates about a certain curve, like this curve, like if this is the center of mass of this body, and you have, this is the curve, and this is the radius rho. So it's rotating about this rho. So when I say omega, I mean the omega of this body is rotating about itself, but here I mean all the body is rotating about a certain point. So if the body is moving on a curve, it will have a normal acceleration. So the omega of the body is 0, but the normal acceleration is more than 0 because it's moving on a curve. So this is for the curvilinear translation, where the velocity vectors are equal at every point. So every point here, 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 all these velocity vectors are equal at any point of this body. So VA1 equal VB1, VC1, VD1, all of the V's on this body at this position are equal. And similarly here, all these velocity, VA2 and VB2, all of these are equal. So let's move to number 3, which is the fixed axis rotation. So for fixed axis rotation, let's assume that this is our body, and this body is bent at this location. So, and if this body is given a certain omega, like let's assume that we have a point A at this body here, and let's draw a line from O at the bend to A, and this body is given a certain omega to move in this way. So the velocity of A, as we learned it from before, VA vector is equal to the omega crossed by the RA vector. So we need to find, this is RA, and we need to find the direction of the omega. You will use the right hand rule. So the omega is going this way. So you will find after this that the direction of the omega is going inside, and this is the r vector. And if you multiply the omega by r vector cross product, so you will go with the right hand rule from the omega to r. So this is omega vector, and this is the r vector. So this is RA, and you go from omega to r, you will find the velocity is pointing this way. So this will be V a vector. And this is actually rational because you know that this body is having omega this way, so this body will be moving this way, so the velocity will be going down. You just like it makes sense. Like after you're getting done with the cross product and you see that the velocity, it doesn't make sense that the body is moving in this way and you got your velocity in the other direction, so there's something wrong. You need to think about it one more time. So the velocity is going this way, and if we get another point P here, you will have, here's A, and this is B, and this will be VB. And VB vector will be omega crossed by RB. Does anybody know, is the VB, is it equal to VA or more than or less than VA?
Should be less than.
Why?
Because the radius is shorter.
Exactly. So yeah, because the body have the same omega, so omega is constant for any point of this body, and the only change is the r. So as we go far from the O, the velocity will be increased. So VA is more than VB, and the velocity keep decreasing until you get to the fixed axis rotation, the fixed axis point here, where the velocity is equal to 0. So the velocity will be something like this. So this is VA, and as you go to the fixed axis rotation point, it will be 0 at this point because my body is fixed here. However, each point on this body for the fixed axis rotation has different velocity, but they have the same omegas, they have the same angular velocity. That's why let's make a note here, the angular displacement theta is the same for any body, for any point on this body. So this actually makes sense because if you have a circle and this is the center of the circle, and you have, like, let's assume that this is a circular body, like a desk or something. And we have a point O here, and we have a point, let's assume that this is point A and this is point B. Let's assume that as the circle is rotated with angle omega, that makes the B comes here. So this is B dash and this is A dash. So the angular position theta, the change in the position theta, is the same for A and B, even they are at different location, because the body have the same omega. But the velocity at A is bigger than B because they have different radius. So this is the note here, that the linear velocity V increases as a function of R, as we showed here. So this is for the fixed axis rotation, and let's move to the last one, which is the general plane motion. So for the general plane motion, you will have your body something like that, and it became something, it moves like this. So here's point A, so let's assume that this A comes from here, and this B comes like this. So you will have VA started something like this, become something like that, VA2, and this is VB1, and let's assume that this is VB2. So the body is just like it translate and rotate. So to pose, so it's something like a combination between translation plus rotation. So this is how the different motion look like, and we will just like I'm making an introduction, and we will be like taking each one of these and analyze the different motions of the rigid body. Does anybody have any questions so far? Rigid body translation. Okay, so let's move to the second section in this chapters, which is talking about the rigid body translation. Oh. Hello?
Hello?
Hello. Uh-oh.
Can you hear me now? Hello?
Hello?
Oh, so you hear me, right?
Yeah.
Yeah, okay, I can hear you now.
I'm sorry, just like a technical thing. All right, so let's get to chapter 16.2, where we are talking about rigid body translation. So let's assume that we oh. Hello.
Hey,
I'm sorry, I don't know what's happening.
it's fine.
Okay. I hope it will not do it again. All right, so for rigid body translation, we have x-axis and y-axis, and we have, let's assume that we have our body here at this location, and we have point B and point A, and we need to identify the velocity of this body and the acceleration at A and at B. Just like go to stop sharing. Hello back. I don't know what's going on, but I'm doing my best over here. So can you see my screen now?
Yep, there it is.
All right, so let's get back here. So yeah, let's move back to the rigid body translation. So for rigid body translation, if we are having our rigid body AB at this location, and we need to identify the position of A with respect to B, or the position of the whole rigid body and the velocity of all this rigid body. So we know that for rigid body, if we have it like this, so the position from point A to point P is not a changing, like because it's rigid. Like as soon as this body is melting and expanding or shrinking, so the points are going towards each other, but this will not be rigid body anymore. So let's draw a vector from point O to A, and this will be RA. And let's draw another vector from point O to point P, and this will be RB vector. And we will have another one from A to B, and this will be RB with respect to A. So RB with respect to A is still a vector. And if we want to get RB vector as we'll learn it from relative position, so this will be equal to RA vector plus RB with respect to A. So this is the position of B is equal to RA plus the position of B with respect to A. And if we want to get the velocity, we will differentiate with respect to the time, and we will have VB vector will be equal to VA vector plus DDT of the RBA vector. And from rigid body concept, that RBA will never change, even in magnitude or direction. So in magnitude, definitely, if it's a rigid body, the magnitude of the position of A with respect to B will never change. If it changed, that means it's not a rigid body and it has deformation. But in direction, for a linear or rectilinear translation, the direction from point A to point B will never change. If change, that means that the body is rotating. So like if this body move, for example, here and point B came here, that means that this body is rotating, and this is not the case. We are dealing with rigid body translation. So the time rate of a change of RB with respect to A is 0, and this is true for rigid body and translation motion. So we will have, as we learn it, that VB vector will be equal to the VA vector. And if we take another time derivative, ddt, so we will end up with that the acceleration of B will be equal to the acceleration of A. And for rigid body translation, the velocity and the acceleration are the same for every point on the body. And that's what we learned from a previous example when we were discussing translation, rectilinear translation. And the omega is equal to 0, and the alpha is equal to 0, and the normal acceleration is equal to 0 as well. So this is for the rigid body translation. And for chapter is talking about the fixed axis rotation. And the fixed axis rotation is much more complicated than the rigid body translation. So let's spend some time explaining how the fixed axis rotation motion look like and how can we describe it. So if we have a body, let's make it something like this, and this body is, let's assume that this body is moving about a certain point. And this body is moving And if we take a cross section in this body here, it will be a circle, something like this. And this circle, let's assume that we have in a y-axis in this direction, in x-axis in this direction, in z-axis in this direction. And this body is rotating, something like this. So let's define what is the motion characteristics for this body, but first I would like to have a bigger circle here of this cross section to explain our motion. And if we are looking from the top view, it will be, here's the y-axis and here's the x-axis. Okay, so let's describe the motion step by step. So angular motion, so for the angular motion only happens for rigid body or lines, but if you have a particle, a small particle, it doesn't have any angular motion, it just can make translation. So angular motion is true for lines and rigid bodies. This is for the angular motion, and let's get to the angular position. So when we describe the angular position, we use theta. Like if we want to describe a point B on this body, like a point B here, and so we draw a vector R from point O to point B, and we measure theta from the positive x-axis. So the angular position is defined by the theta measured from a fixed reference. So this is the angular position. And actually, we can make it angular position and angular displacement. So let's have angular displacement. So for the angular displacement, if we want to, like, if we have this body move from B and make like a small angle, and this angle is d theta. So like, let's assume that this body is rotating in this direction. So it will have an omega and alpha in this direction. So this body is moving like this. So the angular displacement is described by d theta. D theta. The next thing is the angular velocity. So for the angular velocity, we say it omega or theta dot, and this is the time rate of a change of the angular position. So d dt of the theta, and this is how we write it. And the angular acceleration alpha is equal to omega dot or theta double dot, and this is equal to d square theta dt square or d omega dt. So this is how we can describe this motion. And if we have it here, so if we have point B here, and this is the position with respect to theta, and if this body, so it will move d theta. And if we want to describe the linear displacement of the particle B and how it moves, so this is the linear displacement of particle B. And this is equal to the radius multiplied by d theta. We call this ds. And this is equal to r d theta. The radius r multiplied by this d theta, and actually we learned this from before. So with this, let's see what is the equations that we have, which will be similar to the linear acceleration and the linear velocity. So right now, this is the equations that we have. Let's write them here. We have, let's have here theta and omega is equal to d theta dt, and alpha is equal to d omega dt, and also we can have alpha as d omega d theta and d theta dt. Using chain rule, we split these into two, so when you multiply together, so the d theta will go as d theta and you will end up as d omega dt, so it's true. And this actually, this part, d theta dt is equal to omega, so this will be omega d omega dt, and actually this, sorry, d theta. And this is similar to what we learned from before when we say for this one that v is equal to ds dt. So now as we have angular description, so it's d theta dt, and alpha is d omega dt, which is similar to the acceleration, is equal to the time rate of change of the velocity. So, but right now, the angular acceleration is the time rate of change of the angular velocity, and similarly this equation. And from this, we go by differentiation, like, d dt, from here d dt. Sometimes we will need to use the integration form of these equations, like you will have omega dt will be equal to d theta, and you will have to integrate from theta 1 to theta 2, and from t1 to t2. And similarly here, you will have alpha dt will be equal to d omega, and you will integrate from omega 1 to omega 2, and from t1 to t2. In this one as well, it will be alpha d theta will be equal to omega d omega, and this will be integrated from theta 1 to theta 2, and from omega 1 to omega 2. And this is also similar to the linear equations. And if we have a constant, for linear we say constant acceleration, but here we will say constant angular acceleration. So our equations will be omega, when you integrate this one, so it will be omega naught plus alpha constant. So we say here alpha is equal to alpha constant, the angular acceleration is constant, and this will be multiplied by t, and theta will be equal to theta naught plus alpha constant, sorry, plus omega naught t plus the constant alpha multiplied by half multiplied by t square. But actually if we have t naught, so we'll be having t minus t naught square, and this actually will be t minus t naught. But if t naught is 0, so you can take it out. And the final equation that we will have is the omega square will be equal to omega naught square plus 2 constant alpha t minus theta naught. So this is how the equation look like, which is completely similar to the equations for the linear, but we change it v with omega and a with alpha. So it's the same thing. So just like if you are in the exam and you'll have to use these equations, either derive them from the integration form, or the easiest way is to look into the dynamic sheet and change v with omega and a with alpha and S with theta. So it's similar thing, like let's put theta, omega, alpha is corresponding to S, V, and A. So it is the same thing. Okay, so with this, let's see how can we describe the linear motion in terms of the angular format of the velocity and acceleration. So let's move to motion of point P on a rigid body. So let's draw this again. Okay, let's assume that we have our body that has a mechanism down in blue that allows this body to do some kind of rotation, like this body, something like this. And this is our cross section. And this is Y. This is X and this is Z. And this body is making an omega in this direction. Actually, you have omegas going this way, so the direction of the omega in the positive k hat. So if we have our point B here, and the point B came from here to here, so it makes, like, let's say that this is R vector, and our point came at this location. So the first thing is that what we learned from before, if this is d theta, and this is ds, ds will be equal r d theta. That's what we have learned from before. And if we want to describe the v of point P, which will be equal to ds dt, this is linear. We are talking about linear, not radial, not angular velocity. And we know that ds is equal to r d theta over dt. R is constant, so it will be r d theta dt. And this is what we know from before, is the omega multiplied by r. And this is actually nothing new, just like that we know from before, and this is how we get it. And this is the scalar form. So let's get the vector form. So the vector form V is equal to the omega vector crossed by the R vector. So as we know from here, we have R is going, here's the R vector, and we have omega is rotating this way. So here's the omega vector. So it's like rotating this way. So this is the direction. And if we want the direction of the V, we will curl our finger from omega to R, and it will gives you that the V is going this way. Here is the V vector. So the V of P, like, and I'm making all of this, this is point B. I'm making all of that at point B. So the V of B is going this way. V at point B. And actually this is true if you multiply the omega of the body by the R vector measured from any point on the fixed axis. Like if you measure the R from here, like if I make my point here and I here, and let's have our vector R be like this. So the V, let's make this V at B. So the V at B will be equal to omega crossed by RB. And if you do this multiplication, actually they will be equal. Omega multiplied by R is the same by omega multiplied. Even they have different magnitude RB and R, but you know that the magnitude of VB is equal to the magnitude of the omega multiplied by the magnitude of the RB multiplied by sine phi, the angle between these two vectors. And this angle will keep it changing if you like get the R from here or the R from any point. And finally, it will end up with the same thing, like the sine phi is this angle. And if you get RB as a magnitude sine phi, this will give you this R. Like you have a triangle, here's R, and actually this angle is perpendicular, and you have RB something like this, and this is angle phi. So RB sine phi will give you the magnitude of the R here. And if it's like a bigger one, something like that, and this is a different angle phi, it also will give you this R, because phi is keep changing to make it like equal to the R. So finally, what I would like you to know that the V is equal to the omega crossed by RB, or R will not make any difference. So this is the main equation of the velocity at point B. So if we need to get the acceleration at point B, so we will have to take the time derivative of the velocity. So let's memorize what we learned from before. Let's get the A vector. So right now I'm moving from alpha and omega to V and A of a point on the body. So we will have the V vector dt. And if we want to get the time derivative of V, so we'll have to differentiate the first term, d omega dt, and multiply by the second term cross product plus the second term cross product by the derivative of the second term. So this will be equal, you know that the d omega dt will give you alpha, and this will be cross product by R, and this will be plus omega, and you know that dr dt will give you the V vector of the body. The time rate of change of the position will give you the velocity vector. And we know that the velocity vector from here, this equation, this will be crossed by omega crossed by R. So this is how it looks like. And we know from previous that the first term, which is the time rate of change of this one, is the tangent. Let's make it a different color so it can be clear. This is A tangent, and this is A normal. So A tangent is equal to, and this is vector, is the alpha vector crossed by the R. And the A normal is the omega vector crossed by the omega vector crossed by the R vector. And let's see how this looks like. If we, let's have the circle outside. And let's have, this is the y-axis. And this is the x-axis, because if I'm looking from the top side, this will be how it look like. And we have a point P here. And let's draw a vector from this point P. Okay, let's lay out the velocity and the acceleration. For the velocity vector, we have omega, we have it like this, and that's what we got from here. At point P, it will be, as we have omega in this direction. So the VB, the V tangent, and always tangent. So this is the VB vector. Let's just see how does the acceleration look like. So if we have alpha, so this is omega, and if we have alpha is moving in the same direction with omega, so we will have the, let's make it blue. The A tangent will be going this way. Sometimes this is my rigid body. It rotates in this way, but with decelerating, like it's decreasing its speed. So the alpha will be in opposite direction. So the acceleration will be in the opposite direction of the velocity. But if the body is accelerating its rotation, so the alpha will be in the same direction with the omega, and we will have the A tangent will be in the same direction with the V tangent, and the normal acceleration will be towards the center of the curvature. So this is the AN. So let's actually see how these directions look like, how it works. Okay. So right now we have alpha. So let's assume that the alpha, let's make, and let's have alpha is moving this way. The body is rotating this way. So the direction, let's say this is alpha, and the direction will be this way because right hand rule is going this way. And the point P is something here. And this is RB. And this is alpha. So if we cross product the alpha by R, so it will give us the A tangent is going this way. And this will be similar in the same direction of the velocity that we got here. But if the alpha is moving in the other direction, like it's going down, like let's assume that the alpha is going down and the body is rotating in the other direction. So if I'm going from alpha to R, so it will be in the other direction. This will be the A tangent direction. So A tangent could be this way or this way, depends on the direction of the alpha, like if the body is accelerating or decelerating. So this is the confusion about the A tangent and how it's the direction, but actually it's not confusing because if the body is accelerating, so the tangent acceleration will be in the same direction with the tangent velocity. And for the normal acceleration, it's always going to the center. And let's approve the direction here. So actually, if I want to get the scalar format of the AT, it will be alpha multiplied by R, and you can identify the direction using the right-hand rule. And the A normal, the scalar of the A normal, it will be omega square R, and that's what we learned it from before, because omega R is equal to V, and you will have, omega R is equal to V, yeah. And let's make it omega square R square over R, which is similar to this one, and this will be equal to V square over R. That's what we learned from before, but right now we need the direction of the AN. So the AN is equal to omega crossed by omega by R, which is the V vector. So let's see where is the V vector is going. So, and that's what we get it from before. So here's the V vector this way, and this is the omega vector. Let's do cross product between the omega and V. So cross product between omega and V, you will move your curve of your finger from omega to V, so your finger will be going in this way. So when you cross them, cross product, it will give you, this is the AN direction. And it is always in the negative direction of the R vector. So as you can see, the R vector is going this way, the AN is going in the opposite direction. And this is actually true. Like here in this circle, as you can see, the R vector moving from this point, it's going this way. But the AN is going toward the center of the curvature. So we can replace this, that omega, that the normal acceleration will be equal to omega square r as a magnitude, and it's always in the negative r hat direction. We already know it will be always in the negative r hat. Does anybody have any questions so far on how can we move from angular format to linear format of the motion? All right, so let's do some applications on the right-hand rule just to make sure that you guys are following up with me. So we used the right-hand rule so far in two different things. We used it with the angular motion, like you have an omega that is rotating, so we go curl our finger in the direction of the rotation to get the omega direction, something like this. This is omega, and so we are moving from curved direction to linear, so this is the direction of, sorry, should be the other way. So when we curl our finger like this, it will be going down. So this is the omega direction. And we also use the right-hand rule with the cross product. So with cross product, when you multiply a vector B by a vector C to get a vector A, so you will have, let's assume, this is our plane, and you have a vector B like this and a vector C like this. So you move from vector B to vector C, and you will end up with that the vector A will be going down. But if you multiply C by B, the vector will go up. So with this, let's assume that we have this rigid body, and this rigid body is bent at this location, and this location is O, and we have a point A here at this body, and we know that the omega of this body is moving this way, so this is the omega direction, and this is the alpha direction. So we need to know how is the velocity vector direction and the acceleration vector direction at point A. So let's do it together. So first, I will draw a vector from point O to point A to know the direction of the R. So this is RA vector. Does anybody know the direction of the velocity vector? Is the VA is going this way or the VA is going this way? Anybody know the answer?
Would it be going in the direction of the angular velocity?
Yeah, is it right or left?
Or going right.
Okay, yeah, that sounds right. You can use the omega. You know that this body, the omega is moving this way, so the V will be going with the omega direction. And also you can use the right-hand rule to get the omega direction. You know that omega is curling this way, so you can have the vector of the omega like this, and then you multiply omega by r, like cross product, so you will go from the omega vector to the r vector, so you will be knowing that the velocity is going this way. So either are fine. So this is the right VA direction, and this is wrong. So how about the tangent acceleration? Is the tangent acceleration is moving? So this is VA vector, and let's move the tangent acceleration. So A tangent is moving this way or moving this way. Does anybody know the A tangent, the direction of the A tangent? Okay, so for the tangent direction, it's related to the omega because we know that the A tangent, is related to alpha, is alpha crossed by R. It's similar like when you say V tangent is omega crossed by R. So the alpha is rotating this way. That means that, yeah, the body is moving this way, but decelerating. So that means there is something is trying to stop this body. So it's going in opposite direction. So the A tangent is moving this way, and this is the right answer, and this is the wrong answer because it's moving this way. And the last thing is the A normal. Is it moving this way or moving this way? Does anybody know?
Should be moving down.
Exactly. Why? Because it's always going to the center of the motion, and also if we know that's always in the negative R direction. So we know that R is moving up, so it will be going down, and you can also have this from multiplying omega by V. So we know this is the omega, and this is the V direction. It's in plane. Okay, so omega is going this way, and actually this is perpendicular to the V because V is in the plane like this, and the omega is going inside the plane. So if we cross the omega by V, so it will be going down. So this is the direction of A. You should be able to use the right-hand rule to identify the direction of the normal acceleration, tangent, omega, V, all of these, because this is exam problems and this is like usual routine to solving the problems. So you will have to able to do this cross product. So this is how to solve the directions of the velocity and the tangent acceleration and the normal acceleration. So this will be how is the direction look like. So this is what I have for now, and tomorrow we will be moving forward, solving some applications on the fixed axis rotations, and we will be handling what is known the instantaneous center of zero velocity. So does anybody have any questions so far on what we have been explaining? All right, guys. See you tomorrow.
Thank you,
See you.
Professor.